Hello everyone, I'm Dan, and yes, my room is messy because I'm reconfiguring some stuff, but that's not what you came here for. So... A key component to performance in the modern day era is multi-core performance. It's all well and good if your game runs fast on one core, but if it runs fast with all the work distributed across all of your cores, then you can get more work done. So, since we just implemented a physics engine that needs to be updated regularly, I decided to put that on another thread. Of course, the caveat here is that I now need to manage access to the game state much more carefully, because if one thread is writing to the game state while another one is reading, then you get nonsense. By pure luck though, I've already done most of the work here. Notice how the game state is separate from the render state? There's actually only one time where I need both the game state and the render state at the same time, and that's when I'm updating the render state to reflect what's in the game. So for example, meshing chunks, etc, etc, etc. At all other times though, they are completely separate and can be completely separately updated and worked with, which is fantastic. So all I needed to do to make this code multi-threaded was to mediate access to the objects using mutexes. What that basically means is that only one thread is allowed to access the object at a time, and the other thread has to wait while one thread is doing its work. Apart from that though, it's identical code, which is honestly a bit of a miracle. As a result, you can now see we have two printouts here. First one is a frame rate, which just goes as high as it goes, whereas the other one is a tick rate, which tries to be a constant 20 ticks per second, which is much better for consistent physics. Speaking of physics, our physics currently looks quite choppy, and that's because it's updating 20 times a second, whereas you're watching it at 60 frames a second and I'm watching it at 144 frames a second. This discrepancy basically means that the physics looks choppy, and that's kind of a bad thing. To solve this problem, I'm going to smooth out the changes over the course of one frame rather than just applying them instantly. So instead of having choppy movement, we're going to have linear interpolation from the previous position to the new position. To do this, I added a method onto AABBs called lerp, which basically takes one bounding box, another bounding box, and just smoothly transitions between them by some ratio. Then, when we call into our rendering code, we can calculate a subtick value, which is 0 at the start of a tick, 1 at the end of a tick, and some fractional value in between. It can also technically be more than 1 if a tick is going late, but that doesn't really usually happen. We pass it into our rendering code here, and the rendering code can use that in order to interpolate between the previous AABB and the next AABB. And you'll see when we do that we get shockingly smooth results. It looks far better than 20 frames a second. It's not perfect though. There is a slight slowdown before landing, which looks a little weird. But it doesn't bother me too much, so I'm not going to do anything about it for the time being. So we're almost ready to make our game first-person compatible. There's just one small problem. Input. There's simply no way that we could do inputs at 20 ticks per second, because players are far too sensitive to input latency, especially for things like mouse motion. There is a reason why nobody would buy a 20Hz gaming mouse. So, to minimize input latency, I now calculate the camera angles directly in the input system. That means that the very moment you move your mouse, we translate it directly into a camera angle. The camera system then reads the angles directly from the input system, which means that the moment the next frame is being rendered, your inputs have already been applied. When we boot up the game and just start looking around, it's very, very responsive, because it's just going through the input system, straight to the camera system, and onto the screen. There's absolutely minimal latency. And finally, now that we're tracking all of this in the input system, we can simply hand off snapshots to our game logic so that it can orient the player to match the inputs. Finally, we're ready to implement the player controller. As you can see in this tick function, I'm adding some forces for jumping and for moving. I'm also setting some friction, which I also added to the rigid body, and we'll just see how this turns out. So first things first, let's see if we can jump. Yep, that's all working great. And movement, oh wow. Oh, okay. Movement's a bit funky, but it broadly works. It's looking good. Can run up into blocks and oh, oh dear. That's not good. You run into this side, it's not a problem. Oh my god, this friction is horrible. I am veering off to one side whenever I walk in a certain direction. Ah, I see. So the collision handling for negative faces is not working, but for positive ones it should be fine. So yeah, it's a janky player controller, but we have one now, and that means that we are one step closer to a working, minimal, viable prototype. Anyway, I'm going to go edit this section of the video, then I'm going to go to bed because I've been working on this all day. I spent this afternoon fixing many of the physics bugs that I found yesterday. For example, now when you walk diagonally, the drag won't pull you in a certain direction, the drag just works in the direction that you're moving. The walking controls are a lot tighter now because instead of applying acceleration, I now make it try and match a target velocity. And of course, you can now collide with all 4 block faces and you can slide along them just like you would expect to be able to do. Throughout this process, it was really important to me that I made sure whatever I was doing was physically consistent. I wanted to make sure that the physics made sense and I wasn't just bodging numbers to make things work. One of my criticisms of Minecraft's physics system is how the physics is different for like every single entity in the game. Like falling sand literally has half the gravity of the player. Like, how does that make sense? So in an effort to make this game feel a lot more unified, I want to make sure that everything is using the same physics and that it is sound physics. Admittedly, there's only so far I can take that concept, because we are using a physics approximation for performance reasons, but it's still good to be principled where we can. So now that our player is up and running, quite literally, let's talk about placing and breaking blocks. The first problem we immediately run into is that we don't know where to place or break these blocks, because we don't know what block face the player is looking at. The way that we're going to solve this is by using something called a raycast. We're going to start at the camera position, and we're going to move in the direction of the camera until we hit a solid block. That way we know where to break or place our block. However, as with everything in the project, this is much more complicated than it first appears. So to simplify things, the first thing that I implemented was a way of just traveling through 3D space. This code tells you every single time that you pass over a boundary between 2 adjacent grid cells, which you can imagine being like passing over a block boundary or a chunk boundary or anything else that can be represented with a grid. This is what the output of that code looks like. So you can see here, this is where we started and this is the direction that we're going in. And you can see that it's traced out this path of blocks here. If you look closely, these white points are where it's detected that we've passed over a boundary. So you can see there's one here, there's a couple here because there's 2 boundaries here. And you can see it continues like this all the way down in a perfectly straight line. Using that general raycast, I could build this function which does a raycast against all of the blocks in a single chunk. What we do is we just go through 3D space, but instead of just returning positions, we're actually returning specific blocks inside of the chunk. We can use that same general raycast function in order to find all the chunks that line up in a specific direction, which will become useful in the next function. This next function is kind of meta, because it raycasts through the chunks, like I mentioned before, but it also goes into each chunk and raycasts through all of the blocks. The end result is that we can do a raycast over the entire world. Normally, this would have been a nightmare to build, but because I made it using Rust's iterators, it was actually a dream to assemble. It's shockingly simple. So, to summarize, those are the functions that will tell us what block face the player is looking at. Our next problem then is how exactly to communicate this information to the player. We could just draw a dumb crosshair in the middle of the screen, but it'd be quite nice to actually outline the block itself, a bit like Minecraft. However, this presents us with an interesting dilemma. Remember that to raycast through the world's blocks, we need access to the game state because that's where the blocks are stored. However, to respond to inputs as soon as possible, we're going to want to raycast when the inputs come in, which means every single frame in the render loop. The problem then is that the render loop doesn't have access to the game state by design because the game state is updated in the background and just reconciled in every so often. My solution is to capture the immediate vicinity around the player and store it in a nearby state. When we're reconciling the render state to match the game state, we can clone this small area of world and we can keep on using it as the game state gets updated in the background. Specifically, we can raycast against this nearby state in order to find what blocks the player is looking at. With all of this in place, you can see we can now raycast through all of the blocks in our immediate vicinity, and you can see that whatever block we're looking at, even through the ground, gets highlighted in yellow. And since we have block information, we can skip over all of the air blocks and just find the first solid block. We have a sort of hitbox. I'll take over from here. You've done a very good job with your physics and raycasting. You've been on topic for so long, I'm honestly surprised. But there's something we need to talk about. Your build is taking 13 minutes. That's 13 minutes of your life. You're just sitting there watching the computer, waiting for something to happen. Do you think I'm just gonna sit there and let that happen to you? No, of course not. So I don't care what you want to do right now. I don't care what your overarching goal or plan is, because I'm your hyperfocusing side and I get the last say. You will spend the next few hours optimizing your project. You will spend the next few hours reading faster than Lime articles about why build times get really slow. You will spend hours upon hours dividing your project up into modules that worsen your compilation time. And you will eventually realize the entire reason your build was so slow was because you were running it off of an external hard disk. But trust me, you might hate me now, but you will love me in the long run. Stay inattentive. My work is done here. All we have to do now is turn mouse clicks into blocks on the screen. That's not too hard to do, but I do want to take a second to talk about how our input system works. Imagine we're making this game for an arcade machine. Arcade machines come with their own little panel of controls, and we can control what format they are, what they're labelled, etc. For example, we might have a trackball that we use to look around, and maybe we have a few buttons labelled like jump, attack, interact, that sort of thing. This is the universe in which our game operates. It doesn't know about keyboards, mice, gamepads, or anything like that. It just knows the arcade machine cabinet. Here's the player movement code. Notice how it's given an input snapshot here, and the input snapshot can be queried for things like jumping. If you actually take a look at what input snapshot is, you'll see all of the buttons on our arcade machine. At any time, we can ask for a snapshot of what the current inputs look like. So, what angle are we looking at? Are we trying to move forwards? Is the jumping button held down? A bit like you took a real picture of the arcade machine's inputs at that exact moment. So that's all well and good, but where do those arcade machine inputs come from? After all, I'm not running this on an arcade machine, I'm running this on a desktop. That's where input providers come in. The idea of an input provider is that it provides those arcade machine inputs by reading in other signals and converting them. The one I've been using so far is called Key Mouse Input Provider. This basically takes in keyboard and mouse events from the operating system and converts it into arcade machine inputs. It has all sorts of methods to do with mouse motion, keyboard input, and even mouse clicks now, as you can see here. And of course, you can ask it for a snapshot of what the arcade machine inputs look like at this current point in time, and it will give you it, no questions asked. Doing things this way makes it really easy to add new input types, because we don't have to worry about updating all of our game logic. We can just change where the arcade machine inputs are coming from. The reason I bring all of this up is that this arcade machine system does not currently support events. There's no way for us to only run code when someone pushes the button down. We can only observe that the button is currently pushed down. So I decided to add a kind of event called a player action. You can imagine this as something that happens at an instant in time, like attacking something or interacting with something. This code here just turns a snapshot into an event. So if you're pushing the attack button, then it turns into an attack event, interact button turns into an interact event, that sort of thing. If there's multiple possible interpretations, then it just doesn't return anything. Then in the input loop, what we do is, after processing an input event, we then send a player action down to another thread which will handle all of the actions. The action thread itself is pretty simple. When it receives a player action from the main thread, it'll just keep on repeating that action at regular intervals until it receives a new one. The reason why we're doing this in its own thread rather than doing it on the main update thread is so that we're not bound to that 20 tick per second cycle, because, as we said before, input latency is really bad at 20 Hz. We want to be responding to new inputs as quickly as possible so that the user always feels like they're directly in control of the game. Then here in our game state, I added a new method called perform player action, which, as you can see here, is responsible for performing the player action. In this case, when we attack, it does a raycast, it finds what block we're looking at, and then it sets the block to air. And similarly for interact, it finds what block we're looking at, and then it finds the block in front of that and sets it to a solid block. And just like that, we can now place blocks and we can break them. Just as simple as that. And with that, we have arrived at the minimal viable product. This is perhaps the smallest version of the game we could possibly construct, but it has everything that we need. It has the multi-threading, the physics, the graphics, the meshing, everything we need, all in one package. So all we need to do now is build on this strong foundation to create the game of our dreams. Though something tells me we might not have time for all of that in this episode.